Now, in the figure, so actually that particular figure was taken from John Couples because I'm following through the discussion of John Couples on the different modes of diffusion. And now we're just simply on the diffusion in gases, or how diffusion happens in gases. Now, in the case of molecular diffusion of gas A through a non-stagnant or non-diffusing gas B, which is said to be stagnant, meaning it's not moving. So you have here in letter A, your sample is your liquid benzene, and you have air here. So this is your stagnant non-diffusing gas. Your B is your air, and this is your diffusing gas, which is benzene. So the process of diffusion is from this particular point here, PA1, where you have the partial pressure of A here as P sub A1, labeled as P sub A1, to PA2. Now the partial pressure of A in your non-diffusing stagnant air, which is B. Now, another scenario is in the case of ammonia in air, now being absorbed into water. So your ammonia, which is actually a contaminant when it's present with your air as a mixture of ammonia and air. Ammonia is the contaminant then, and your ammonia is being absorbed in the liquid water. So the process of absorbing ammonia to water is for the ammonia to be separated from this air here. So this is another example of your scenario wherein your ammonia is diffusing to your liquid water. So your stagnant here, in this case, the stagnant medium here is water. It's getting absorbed into water, and ammonia is getting diffused through your liquid water. But our example here specifically is on letter A, wherein we have two gases. One is benzene and the other one is air, and benzene is said to be diffusing to a non-diffusing stagnant air. So this is our sample problem here. Now, for this scenario, we have to determine first, so that we will know the flux and sub A, we need to determine here the log mean of B. And that's the partial pressure of B, but it's the log mean of that. So the M here means it's mean, or specifically log mean. And you need to determine, in this case, the partial pressure of A or B, depending on which of the two formulas you will utilize, in points 1 and 2. So the points 1 and 2 that is being referred to in here is this one, point 1, and this is point 2. So point 1 is on your diffusing gas, and point 2 is in your non-diffusing gas, or in your stagnant gas. Now, if you have that particular partial pressures and you have the total pressure of the system of the two gases, then it would be a simple case of substitution to get the log mean pressure of B in that case. Now, if you don't have the A and we want to use the B, actually the B can be taken from the context that PB plus PA is equal to P. So if you have PA1, or if you don't have PB1 and you have PA1 and the total pressure, then you can subtract PA1 from P, and that would be your PB1. So either which, you can get the value of the log mean of P sub B here. Why get the P sub B? Because you need it here in the formula below, together with the molar diffusivity of A to B. So with A diffusing to B, so this one should be given by the problem, the molar diffusivity, and this is the total pressure. This is the universal gas constant. This is the absolute temperature. This is the distance, or the diffusing path, or the length, or yes, the distance in which a molecule of the diffusing gas is to traverse to, going to the non-diffusing gas. So that's your Z sub 1, Z sub 2 minus C sub 1. And these are your partial pressures of A at point 1 and point 2 respectively. So you need the log mean PB in here. So if you have that and you can substitute it here, then you will have already the flux. Now, in most of the problems in diffusivity class, or in diffusion related problem, the key is always knowing the formula to use. and knowing the condition when such a formula should be used. So this is a formula, this is a set of formula that you will use for the scenario in which it is stipulated in here or specified. So now let's go to the sample problem that we have concerning the application of the two formula. So it's actually a sample problem also in John Copley's because it's also referring you to a particular figure which he used to discuss the principle or the scenario or the phenomena of diffusion of A to B. So water in the bottom of a narrow metal tube is held at a constant temperature of 293 Kelvin. The total pressure, assumed dry, so meaning it does not have water vapor, is 1.01325 times 10 raised to 5 Pascal. And this is actually normal atmospheric condition. And the temperature is 20 degrees Celsius, and this is the equivalent in Kelvin. The water evaporates and diffuses through the air in the tube, and the diffusion path or the length in which water diffuses through is 0.1524 meters, or that's equivalent to 0.5 feet long. The diagram is similar to figure 6.2-2A, which I have discussed. So your diffusing gas is diffusing to a stagnant gas. So that's A. Calculate the rate of evaporation at steady state in pound mole per hour feet squared. Now, if you have this, you can just have it converted to kilogram mole per second per meter squared. So the diffusivity of water vapor at 293 Kelvin and 180 M pressure is given to be 250 times 10 raised to negative 4 meters squared per second. Now, you are to assume that the system is isothermal, meaning throughout the diffusion process, there shouldn't be any changes in this temperature of 20 degrees Celsius. Now, since the problem is asking for both sets of units, the English and the SI set of units, then you are to use both unit systems as well. Now, how do we solve this particular problem? So let me go to the board and just simply go straight to the formula that we can use and the things that we need to do. Anyhow, everything is in here as stated in the problem for us to be able to save some time. My class, I can't see my board. Okay. Okay, do you see my board?
Yes, yes.
Okay, so if you go straight to the solution and since the problem is asking for the rate of diffusion and that's the flux, we will write the formula that will help us solve for the flux. So Na is equal to, let me refer to what's written here so I can save time. So you have the molar diffusivity of A to B, then we have the total pressure of the system. We divide it by the product of RT, and we have the diffusion path, the Z2 minus Z1, the length of the diffusion path, and the log mean partial pressure of B. Then we multiply it to PA1, a partial pressure of A at 0.1 and 0.2. Now we'll check what the problem already provides in terms of the information. So let's see what we need to determine and what we are already given. So in this case, the problem already gives us the molar diffusivity, the unit of which is in meters squared per second. Then the total pressure is given. This we can get from a conversion table. The temperature is given. As for the length of the diffusion path, this is given as well. And for the partial pressures of A at 0.1 and 0.2, that's not given together with the, together with the log mean pressure of B. So in this case, we will need to determine first those that are unchecked. That way we can substitute everything to our formula. So as I have said, you have, a while ago, you have the choice. I'd like to stop sharing here. You have actually the choice of two formulas here, whichever you find simple and direct to the point when you need to solve something. And that formula is this. So either you use this one or you use this one. The thing with using the PB2 is still you're going to need the PA1 and the PA2. So even if you want this, because it's simple, but still you need the PA1 and PA2 in here. So you might as well use this one. Okay, so I will have the PA1 and the PA2 then. So, but still it depends on you whether you would like to use any of the two formula dependent on your sense of convenience, wherever you find easier to do, whatever you find easier to do. Now, we will get the partial pressure of A1, PA1. So the problem gives us PA1. Let me read, where is it? Okay, so in this case, you need to find the vapor pressure. It's not given. That is why I did not check it. It's not given in the problem. So this PA1 should be taken from a table or an appendix in a book. So in your case, you are to get this from, or this is the, from an appendix or a table in your handbook. This is the vapor pressure of, in this case, the gas that we're talking about is water. Vapor pressure of water at the indicated temperature of 20 degrees Celsius, or that's the 293 Kelvin. So if you have your data from a table, this is actually equal to, so I'd like to give this to you. You can read this from John Kublis if you have John Kublis. If not, if you have your handbook, better, because you can use your handbook in determining this particular information. In ATM, you will have 0.031. In Pascal, this is equal to 2.341 times 10 raised to 3 Pascal. Now, your PA, your vapor pressure of A at 0.2, since it's already in the region of the non-diffusing gas or the stagnant gas, this is already 0. Okay? Your PA2 is said to be 0 already because it's in your pure A, so it does not have any vapor pressure there. Now, so in this case, these two are already known. So you can find this, you have this already checked. Then the next thing that you do is determine the PBM, or the lug mean partial pressure of B. So our formula for the lug mean partial pressure of B, if we'll use the easier route, will be PB2 minus PB1, the ln of PB2 over PB1, just like the lug mean temperature difference formula. Now, getting the partial pressure of B, if you know A, it's just like it's the partial pressure or the pressure exerted by B in the mixture of A and B. So if you know already A, so you just get the difference of the two. So in the case of PB2, this would be 1.0 because we don't have A at 0.2. We don't have already vapor pressure due to A at 0.2. So it's all B. So you have 1.0 and we have minus. In the case of PB1, this one should be substituted to, or rather subtracted from, the total pressure which is given in the problem. So if you want to write it here, the total pressure is 1.01325 times 10 raised to 5, and you'd like to subtract this one, the 2.4, 0.341 times 10 raised to 3. This now will be the partial pressure of B. Then we divide by the ln of 1 over the difference of these two, which is 0.9769. Actually, this is in ATM and this is in ATM as well. There's no need for you to convert to Pascal even if you have these two in Pascal. It's because anyway, whatever unit is in the numerator in here, that would be the same unit in the denominator. Then there's no need for you to convert unless otherwise your units are not the same. So if your units here in the partial pressures or in your vapor pressures are just the same, there's no need to convert, whether we're talking about English or SI sets of units. So in this case, if you have already substituted the value, you will have a PBM equal to 1.001 times 10 raised to 5 Pascal. Now having this, all you have to do is substitute it in here and you have already the flux. So you have Na equal to, so if we go back to the previous, we have DAB. Now, your DAB will be depending on the kind of units that you want reflected on the flux. So let's say we'll start with the SI set of units. I will use the original molar diffusivity of 0.250, excuse me, times 10 raised to negative 4 meters squared per second. And this is to be multiplied to the total pressure. Since I have SI here, then I will need to use the SI also. So 1.01325 times 10 raised to 5 Pascal. And then that would be RT. So your R here is 8314. This is mole. What's the unit for this? Wait, what is the R for SI? The appropriate R for SI is 8314, right? So 8314. Then we have the temperature, which is 293. And you have the length of the diffusion path. In this case, sorry, this is already my UO. So the length of the diffusion path is 0.1524 in meters. So this is 0.1524 in meters. This is your Z2 minus Z1. And then you have this one, the PBM. So 1.001 times 10 raised to 5. 1.001 times 10 raised to 5. Then we are to multiply this by the difference in the pressure. So PA, that would be PA1 is 2341 times 10 raised to 3 minus 0. PA2 is 0. So you have already the flux in SI to be equal to 1.595. Kindly check, this is the exact value that is written in the book, times 10 raised to 7 kilomole or kilogram mole per second per meter squared. So this is how fast your A is diffusing to B. Now, if you want to change this to pound mole, there is a direct conversion. If you find it in John Couples, there's a direct conversion for that. The DAB can be converted to feet squared per hour using the conversion of 3.875. So it's just a matter of converting. So your 0.250 times 10 raised to negative 4 should be multiplied to this particular conversion factor. The 3.875 times 10 raised to 4, which converts your per meter second, or meters per second rather, to feet squared per hour. Now, This is already in English. And we want this also in English, the pressure. So this would be 1 atm. I won't write anymore the units. Then your denominator should be in atm as well. So the appropriate R to use is 0.730, and this has a unit of cubic feet, atm per pound mole Rankine. So that's the R. So there's a need for us to convert the 20 degrees Celsius to Fahrenheit, then add it to 460. That way it will be Rankine already. So if you want your 20 degrees Celsius to Fahrenheit, that would be 68. This should be 68, and you add 460. So since this is English, your temperature should be also in English, and that's Rankine. The next that we need to put in here is the meters to be converted to feet. So 0.1524, 1 meter is 3.28 feet. And then what else? We have this one, the Pascal, convert it to ATM. So you have 1.001 times 10 raised to 5. You can convert this to ATM by dividing it by 1.01325 times 10 raised to 5. This converts it already to ATM. This is originally in Pascal. Then we are to multiply this with again, the difference in pressure. So in this case, by the way, this should be still A class, only with a different unit. Why is that? Why did I write it as B? So this one, this is difference of the two in, this one is in ATM. So it's okay. ATM already. Wait, I'm not sure. The 2.3, that's Pascal. I'm sorry. So 0.0231 is the appropriate value here. The one in ATM, not in Pascal, because Pascal is for the English. So this should be 0.02, what is that? 31 minus 0. So ATM. By the way, class, this one here is to be by multiplication. It's not division. So this whole thing here is division, and this one should be written here or in here for multiplication. Your NA and pound mole per hour per feet squared is 1.175 times 10 raised to negative 4. So pound mole per hour per feet squared. Now, if you notice in this problem, it's all substitution to the formula. All you have to do is know the correct formula and the value to substitute to such a formula. Okay, so this is the case wherein you have a gas diffusing to another non-diffusing or stagnant gas. In this case, in the example, we have water vapor. Okay, so I'll go to the next part of the slide. This is our sample problem number 3. So we can now go to molecular diffusion through a varying cross-sectional area. And a case of a varying cross-sectional area here, again, as illustrated by John Kuplis, you have two cases. So diffusion through a varying cross-sectional area. In letter A, you have a case of a sphere to a surrounding medium. And actually, this particular scenario is the one that was used in the sample problem, okay? So if you have a sphere, then it's diffusing from a sphere to a surrounding medium. This is the surrounding medium, and this is your sphere. Now, and letter B, through a circular conduit. So a circular conduit, meaning the cross-sectional area is that of a circle that is tapered uniformly. So there is a tapering here. So the cross-sectional area of this portion, 1, is not the same as the cross-sectional area of this portion. So this is the two scenarios wherein you have molecular diffusion to a varying cross-sectional area. Now, in this case, you will be using this particular formula of the flux again, the rate of diffusion of A from point 1 to this particular point here, to point 2. In this case of letter A, so you have A coming from this particular cross-sectional area, a sphere, to this particular medium, surrounding medium. And in this case, we have A coming from this particular region to this region. And this is your formula. You still be needing the molar diffusivity, and you'll be needing the C sub A1 and the C sub A2, and you'll be needing the diameter, the D sub 1. Okay, to illustrate how such a formula will be used, so we have this sample problem again. So a very classic example of the sphere is the naphthalene balls diffusing through air. Okay, so a sphere of naphthalene having a radius of 2.0 mm is suspended in a large volume of still air at 318 Kelvin and 1.01325 Pascal. The surface temperature of naphthalene can be assumed to be 318 Kelvin, and its vapor pressure at this particular temperature is 0.555 mmHg. Now, the molar diffusivity of naphthalene in air at this particular temperature is given to be 6.92 times 10 raised to negative 6 meters squared per second. Again, we calculate the rate of evaporation, and we're after the flux of naphthalene from the surface. Now, so we'll go to our board again. Okay. So in the case of the sphere diffusing through that particular medium, which is air, so that's a sample of molecular diffusion nga hindi na pareho ang imo nga cross-sectional area. So in that case, you will have a formula that is stated here, the original formula to be used in this case, wherein diffusion is through a varying cross-sectional area, is this. So you have NA equal to N sub A bar divided by A. So what is this N sub A bar? This N sub A bar, I will just read it from here, is the kilogram moles of A, diffusing per second. So this one we will write as kilomole of A diffusing per second per unit time. At steady state, this